Hello, welcome to Ademola, and today we are doing electron structure. Such an important topic in A-level chemistry, because this is why they start telling you that they lie to you in GCSE, yeah? So stick with it, let's get it done. We're going to cover energy shells, we're going to cover subshells, orbitals, the whole lot. Let's get it done. I think the most appropriate way to start off this video is actually an apology, guys. This is why they tell you that GCSE was a lie, and you kind of need to literally relearn everything. Really a piss take, to be honest, but let's get it. So, in GCSE, they would have told you electron shells, first shell 2, 8, 8, 18. That's what they would have told you, yeah? Now we're going to say, completely just bin all of that, forget about it. This is what we need to know now. So, we're going to talk about a bit about electron configuration, which is the arrangement of electrons in an atom, yeah? Don't worry too much about the definition, probably won't ask you on the exam. But here's where we change things up. Now I'm going to tell you, the first shell does have 2 electrons, the second does have 8, but then the third has 18, and the fourth has 32. Cool. Let's let it simmer down, so let it simmer down. I'm going to tell you, guys, fortunately, I would not recommend just learning these numbers. I would recommend just putting it into the formula, 2n squared. No matter what you do, this will tell you the amount of electrons that's in a shell, 2n squared. So for example, let's sub in 3, 2 lots of 3 squared, which is 9, 2 times 9, 18. Yeah? Just use this formula instead of trying to remember things. Cool. What we really want to talk about is, we have an electron shell. Yeah, that's the one you would have seen when we have the atom in the middle, and we've got these electron shells surrounding it. So on my bad diagram. Now we are going to talk about subshells. So electron shells have a subunit, a subshell. And with subshells, we need to know their names. So we've got the S subshell, the P subshell, the D subshell, and the F subshell. So they go up. The S subshell holds 2 electrons, P6, D10, F14. Yeah, I would say, to be honest, you rarely will. I don't think you really will ever come across F. To be honest, I don't think you'll ever come across F. But S, P, and D definitely will come across. Know how many electrons in each. So I'll show a better example later. But the first shell has 1 S. So first shell, that's the number 1, and then S, it has an S subshell. Yeah. The second shell, it has an S subshell and a P subshell. So it's got 2s and 2p. Holds 8 electrons because S has 2, P has 6. The third shell has S, P, and D. So S holds 2, P holds 6, D holds 10, total 18. Yeah? And the fourth, S, P, D, and F. So we got the 2 plus the 6 plus the 10 plus the 14 adds up to 32. Just remember, those are the subshells that we are going to have. Okay. I hope that's not too much of a brain boozler. Sorry about that term. But I hope that's not too confusing. Just stick with me. Stick with me. So the reason I'm begging you to stick with me is because we now need to introduce something else. So we've got the shell, we've got the subshell, and now I'm going to tell you about orbitals. So an orbital, literally, definition, a regional space where an electron can be found. Yeah, that one they might ask. But a regional space where an electron can be found. And each orbital holds a maximum of 2 electrons. So within an orbital, we can only have 2 electrons. Now, this is why we're going to get a bit more complex. So your S subshell has 1 orbital. Like we said, S can only hold 2 electrons, so it has 1 orbital. P has 3 orbitals. And we're literally going to keep going up by 2, so D has 5 orbitals, F has 7. And you can see here, if each orbital holds 2, that's why we got our numbers, that the S subshell holds 2, P holds 6, D holds 10, F holds 14. You can see why we got those numbers of electrons, yeah? It's about the number of orbitals that we have, an orbital just being a regional space where an electron can be found, yeah? Now, orbitals have a specific, unique 3D shape, but your specification, thank God for this, they only ask you about S and P. That's the only ones they want you to know. So we'll learn them. Your S orbitals, spherical, blessed, yeah? Completely blessed. Your P orbitals are dumbbell shaped, so 3D dumbbell shaped. Yeah, and they exist on an X, Y, and Z axis. They are perpendicular to each other. So you can see here in this diagram, we've got a bunch of 3D dumbbell-shaped orbitals on different axes. So the red is on the X-axis, the blue is on the Y-axis, the green is on the Z-axis. Yeah, I'm gonna quickly dismantle it a tiny. Oh no, you'll see it here. This is kind of our hierarchy that I wanted to show you. So you can see the different. This one's Y, this one's X, this one's Z. Yeah, so you're going from left to right. You can see that we've got the orbitals inside of a subshell, which is inside of a shell. So for example, this is the second shell I've shown here, because it's got an s orbital and it's also got a p orbitals. Yeah, so it's got an s subshell and a p subshell. I hope that makes sense. So orbitals are just orbitals, yeah, and orbitals exist inside of the subshell. Inside of the subshell will determine the shape of that orbital. So for example, here is an s subshell, here is a p subshell, yeah. They are just going to be inside of your electron shell. I really hope that makes sense, guys. Please, sometimes you might need to rewind. Just try and soak it in. Just keep trying to soak it in. We're going to add on another complexity to this. Okay, so this is the last bit of theory that we need to add on. Yeah, electrons have spin. I'm so sorry. I'm so sorry that we're adding more. But electrons have spin. And that's literally just the direction it spins in. So clockwise and anti-clockwise. But if it has the same spin, so say we have electron with clockwise spin next to another electron with clockwise spin. If they have the same, they're going to repel. Hence, we said the orbital has max 2 electrons, yeah? Within an orbital, the electrons must have an opposite spin to prevent what we call spin repulsion. And I'm even going to write it there. Spin repulsion. Yeah? That's what we want to avoid inside of the orbital, just because we kind of want it to be stable. Yeah, it's a atom. We want it to be stable. Now, I need to show you how orbitals feel. So, say we've got, for example, calcium. Let's find it on the periodic table. Calcium, for example. I don't want to ruin my example, but calcium's here. Yeah, it's in the 4th period, and it's in the 2nd. Yeah, total has 20 electrons. So we've shown that. Yeah, let's start filling it out. So, we said it has 1s. You're going to put orbital here. So an electron goes into this orbital, and another electron goes in. And you can see here they're going in opposite directions, opposite spin. Cool. I'll just write that we're doing calcium. Now, again, we want to fill up the s orbital. So in the second shell now, we've done the first shell. In the second cell, we're going to do the same thing. Yeah? Same thing. We're filling up the electrons. We're going up each energy level. Yeah? You're going up the energy level. There's more energy as you keep going. Cool. Now, this is where we're going to get a bit tacky. So your p orbitals, now, we have more stability if we fill it like this first. So you're going to put electrons with the same spin, you're going to put them into the orbital. And this is now what we call half full. So this p subshell is half full. There's an electron in each of the orbitals. That is going to be how it feels. It feels like that. And then afterwards, it's going to say, okay, now let's do that. And now we're full. Yeah? So it goes from half filled, what we had. We fill up each orbital. We get 1 in each orbital. That's going to be more stable than filling up each orbital individually. So we do it, 1 in each orbital, half full, and then we finish it off, and we fully fill it. Yeah? Cool. Now, literally, for 3, this is why we have another caveat. Cool. S fills up normally. P fills up. Now, something that you need to be aware of, be very, very aware of this, catches a lot of people out. 4s has lower energy than 3d. What does that mean? It means it's easier for an electron to enter into the 4s than it is to enter into 3d. So, what will happen is, with calcium, is you're going to fill off that p, yeah, the 3p subshell. Then, instead of going to 3d, it's actually going to go to 4s. It will actually go to 4s, fill that up, and then, because 4s has a lower energy level than 3d, it was easier to put electrons into 4s, and then it will come to 3d. Yeah? So that's kind of what you have with transition elements. But that's when they start to fill up that d subshell. Yeah? And literally what you'll see with periodic table, if we highlights, you'll notice that, goodness, sorry about that. These ones I'm highlighting here is called S block. Yeah? These are called S block because it has s orbitals. So we'll just quickly put S there, highlight it in orange for you. Then, this here, let's just move across here. In green, we're going to highlight, this is called P. So this is going to be your P block. Because these ones are when you start to fill out your P subshells. Yeah? In the middle here, your transition elements mostly, this is what we're going to call D block. So again, just sorry about my drawing. But D block, because this is when we start filling out D subshells. Yeah, and then finally down here, and you won't even need to worry about this for A level. This is called F block. So over here, these elements that you never really ever use, to be honest, that's going to be F block. So that's something to be aware of. Something else that we need to talk about is writing electron configurations. So normally calcium, you would just say 2, 8, 8 sorry, talking about 2, basically, you know the normal way you write your electron configuration. I'm sorry, I've actually butchered that. What I'm going to actually show you now is what we do. Sometimes you can go from 1s, so literally just as we did, 1s, 2 electrons in there, 1s2, 2s, there's 2 electrons, 2s2, 2p, 6 electrons in there, 2p6, 3s, 2 electrons, 3s2, 3p, there's 6 electrons, so 3p6, and then there's 2 electrons in 4s, so 4s2. We can also do a shorthand where we'll look at calcium. I'm going to go a period up and find the nearest noble gas, argon. Yeah, so we're focusing on argon. What we'll do is literally argon, and then what do we have to add on? 4s2. Yeah, so I just want to explain that a bit more. This all, if you just left it there, you'd have argon. Yeah, when we add on the 4s2, that's when we have calcium. So that's why we can do argon, just simplify it down, argon, because all that's represented by argon, and then just add on 4s2. Yeah, that means we also need to do exceptions. I'm so sorry, last little caveat. Yeah, exceptions are going to be chromium and copper. Now, what really happens here is that they've decided for some reason that a half full or a fully filled d orbital is going to be more stable than having a full 4s. Yeah, that's what they've decided. Guys, please just accept it. Literally, this is something that you just need to accept. Yeah, that's going to be more stable. So typically in the red, that's what you'd expect. In the red is what you would expect chromium and copper to be if you just follow the rules that we just went through. But having a half full D subshell or a fully filled D subshell is more stable than having that full 4s. Yeah, so they're going to donate an electron from the 4s into the 3D so that you can have a half filled 3D in the case of chromium, or a fully filled 3D in the case of copper. Remember that exceptions, that is something they can very easily ask in the exam. Yeah. Again, I'm sorry if I've lost anyone. Literally, sometimes I feel like I really hate saying this as like trying to teach a concept, but there are some things that you kind of just need to accept and learn. It's just the way it is, and this is kind of one of those things. So if you need to digest it again, just replay parts of the video. We're going to go into questions now, but replay parts of the video if there's something that kind of caught you out. Yeah. Okay, so we're going to put what we just learned to the test. Now, first question is asking you for the shape of your S and P orbital. And then what we're going to talk about is the relative energy from 2s to 2p in a nitrogen atom. Specifically in a nitrogen atom. So get out your periodic table, look for nitrogen. Yeah? That one's going to be a bit more complex, but we'll explain it in the answers. And then just electron configurations, yeah? We've got a manganese atom and a bromide ion. Had to change the question, it wasn't on the mark scheme. So have a go at that. Those are your 3 or 4 questions to try now. Okay, so here are the answers. Now, I'm hoping for the shape, spherical and dumbbell, I'm hoping that those are just things you remembered. Yeah? Now, for this question, it said, describe the relative energy of 2s and each of the 3 2p orbitals. Well, if we look at the periodic table, nitrogen was in period 7, right? So nitrogen, if I am correct here, is going to be 1s2, 2s2, 2p3. And now we'll get you your 7 electrons, right? So there's going to be, again, we're going to draw it out. Apologies for that. Then we're going to draw it out, just so that you can really get this concept. Apologies for bad drawing. But, you know, 1s is fully filled, 2s is fully filled, and then we're going to half fill 2p. So, what do we know? Now, you can see, if we just compare each of the 3p orbitals, so the second part of the question, we can see there's 1 electron in each. So they must be equal in terms of the relative energy. And I'm sure that will be backed up by the mark scheme. Yeah. So the 3p orbitals have an equal energy. Cool. Now, something that I didn't show you before, and we're going to put in a nice diagram, probably to the side here. You need to look at energy levels. So if the y-axis is energy, yeah, what you'll normally see, and I'm so sorry, this is a bad place to do it. We're going to do it in red just to make it clearer. If this is the level of 1s, you'll see that 2s is here, so it's going up. 2p is going to be above that. And literally, you're going to notice it keeps going up like that. So here's 3s, here is 3p. But then, this is where we had a difference, yeah? If we go up here for 3d, 4s is below that, which is why it gets filled first. I hope that makes sense. I hope you can follow that diagram. I've drawn it in a really bad position, but I hope that makes sense. I'll make this a bit bolder so you can see. But just look at the relative energy levels, yeah, for each of the orbitals. You're going to fill from the lowest energy upwards. So the p orbitals, you can see that 2p has a greater than 3, than 2s. I hope that makes sense. And then finally, electron configuration of manganese. Just locate it on the periodic table. Follow the process, yeah? So manganese is one of those transition elements. Just fill it up normally, where you get it to 4s, and then literally just go across. So like, the first one's going to be 3d1, 3d2, 3d3, 3d4. Then you get to 3d5 where it's manganese. And just remember, if we switch it up and it was chromium, you would have to donate from the 4s to the 3d to get it half full. And finally, this one was the bromide ion, I believe. Yeah. So literally, you do as you normally do, get to bromine. Hopefully, at that point, you've got 4p5, yeah? And literally, just remember it's an ion. So you need to add on that one electron that it gained, which is why it's going to be 4p6. I hope that makes sense. Again, any questions, just ask them below. See, I appreciate this is a really complex topic to get your head around. And really, it's where I believe this is when A-level chemistry actually starts, yeah? A lot of the things that you would have done in 2.1 are just going to be follow-ups from GCSE. So literally, with the A-star tips, guys, you need to try and make something like this as simple as possible, yeah? Use the periodic table. Follow it in order. Even if you look like a fool in the exam, putting your finger across like some old man, just do it, yeah? Practice writing out electron configurations for many different elements. Test yourself, literally. Guys, you've got God knows how many elements on that periodic table, yeah? Just practice writing out electron configurations for all of them. Eventually, you're going to start to click. This is how I do it. This is how I do it, yeah? Just make sure you practice. And the shades of S&P orbitals, very easy to forget, but it's an easy mark to pick up, yeah? Now, what do you not do? 4s gets filled before 3d. Remember that, please. And also know the exceptions, yeah? Chromium, copper, those are ones that you can just know straight off the bat. Those are my exceptions when I was talking about transition elements. 4s being filled before 3d. Another one, please, please, please just remember it, yeah? That's all I got for A-star tips. I really do appreciate that this is where A-level chemistry starts to lose a lot of people and it starts to get a bit harder, yeah? So stick with it. If you need to rewatch things, rewatch things. If you need to watch other videos, please do that. This is when we start to do A-level chemistry. So thank you so much for listening. If you found it useful, please like and subscribe to the channel. Any questions, literally, and I mean any questions about any of this, drop it in the comments below. I'm going to do my best to explain it. If I need to try like a different method to explaining it, I will. But just please ask any questions below. We've got the TikTok and the Instagram, both at Ademola, and that will be all for this lesson. So yeah, have a good one, and bye for now.